Hello everyone. So today we're going to look at, um, I guess you could say it's the most trickiest or the most jumbled up amplifier circuit that we've seen so far. So this is the differential amplifier, or you could say it's the difference amplifier. And actually, I guess calling it the difference amplifier is better because just do not confuse this with the differentiator that we'll see later on, hopefully. But anyways, so it's this circuit, and I think you can guess, as we'll find the formula, I think you can guess already that has something to do with subtracting these voltages, something like that, just like we saw in the summing amplifier, the summing op amp. Where was this? Okay, it's gonna take time to find that. But anyways, um, yeah. So what we have here is, so there's one input, one voltage signal input or supply right here. Okay, it has to go through a resistor. We'll call that R1, and you also have, this is the inverting input. This is connected to the inverting input. You have your feedback resistor right here, but instead of R sub F, we'll call that R sub 2 because it lines up with how we are naming these, and kind as when we'll find the formula, it makes it easy to remember that. So this is your feedback resistor, and here you have connected to the non-inverting input, you have again another voltage supply or signal connected to a resistor, and between this resistor and the non-inverting input you have a connection with a resistor which is connected to the ground. All right, and this is your output. All right, these are your output terminals. So this is how it looks. Now we'll try to solve for the output voltage terms of V1 and V2. So that's our goal. So first things first, let's try to I guess identify some nodes. And here actually, unlike what you've been doing in the past few videos, we'll actually need to work with two nodes, as you'll see. So let's see. Um, we have this node. I should have marked that in red. Actually, I'll do that. Okay, I'll call this one node B, I guess, and that one I'll call node A. Okay, so this one I'll call node A. So let's see. Let's try to apply nodal analysis or KCL. Okay, first I'll actually node B looks simpler than what's happening here. So first I'd like to deal with this one. So what we have here, let's see, if the voltage here is V sub B, okay, of this node. Let's see. Wait, I'll change color for this one. So if the voltage is V sub B here, all right. So what we have is, okay, there's a current here, but that's zero. All right. There's there's a current entering here. All right, and there's a current exiting here. All right, there's a current exiting here. Okay, so let's see, let's try to deal with this. So what we have here is, let's see, and yeah, okay, so one thing is, you might wonder why I'm not saying that this current is zero. Well, it doesn't necessarily have to be, especially if we connect this to something else. This current won't always be zero like it's here. Okay, so I'll not do that. But even whether it's zero or not, the way we're applying KCL, it would still be valid. So what we get here is, this current entering is the same as this current that's exiting. Well, plus zero, but that doesn't matter. So the current entering is, let's see, V2 minus V sub B, okay, divided by R3. This is going to be equal to the current exiting, and that's V sub B, minus 0. This whole node right here, this is the ground, so that's why this is 0. Okay, so minus 0 divided by r sub 4, all right. So what we're trying to do actually is solve for the node voltage right here. this is a known value. Okay, v2, whether you get it from somewhere else or something, or whether you get it from a cell, we're gonna assume that we know that. Okay, that's a known expression or value. So what we need to find is actually this node voltage right here. uh, if you want to do that, let's multiply by let's see, let's multiply by R3. Okay, so wait, R4. Yeah, let's multiply by R3, R4. I guess both would be good. Yeah. So let's see. If we multiply by both R3 and R4, what we get is R4. Okay. V2 minus V sub B. Okay. Um, this is gonna equal R3 V sub B. All right, so we're almost done. If we add R4 V sub B to both sides, this one would cancel out. What we get here is R4 V2. This thing goes out. We're basically just moving this to here, so we're adding that. So what we get here is R3 V sub B plus R4 V sub B. We can take a V sub B factor out. Okay, and now just to find V sub B, all we have to do is divide by R3 plus R4. So V sub B is gonna equal R4, okay, divided by R3 plus R4 multiplied by V2. All right. So that is our V sub B. That is our V sub B. Okay, and we also need to remember, okay, this is just, well, we can also deal with that later. We will deal with that later, but just as a reminder, V sub B right here has to be the same as V sub A, right? Because these two are the input voltages, the inverting and non-inverting input voltages, so they need to be equal. Okay, so I'll just write that down for now, that this needs to be equal to V sub A. All right. With that done, I'd like to deal with this node A now. Okay, same thing. We're gonna apply KCL right here. So what happens here is you have a current entering. Okay, here you have a current exiting. I'll use a different color for that. You have a current exiting right here. Okay, and we also have a current here, but that's zero. Okay, so the current entering is equal to the current exiting. So let's see here, it's wait, and this one, this node voltage is V sub A. Okay, so here what you have, the current entering is V1 minus V sub A divided by R1. Okay, so V1 minus V sub A divided by R1. This is gonna equal the current that's exiting, right? This is gonna equal the current that's exiting, which is, I should have done that in red, but anyways, let's see. V sub A minus, and this node right here, the voltage of that is V output. Okay, so V sub A minus V output divided by R2. V sub A B sub A divided by V output divided minus V output divided by R2. Okay, now we're trying to solve for V output, so let's multiply by R2. Let's multiply by R2. What we get is, let's see, R1. Sorry, no, that's not R1. That's R2 by R1. V1 minus V sub A equals, let's see, V sub A minus V output. All right. So if we let's see, negate both sides and add V sub A, we get V output equals, this is negated. So what we have here is, let's see, uh, no, we're gonna have plus V sub A. This is negated, so we have here is, let's see, plus R2 by R1, V sub A minus V1. Okay, I hope this is clear. I just negated both sides first and then I added V sub A. Okay, here you'll get V sub O, V output minus VA after negation, and then we just add V sub A to just get our output voltage. All right, let's simplify this a bit. let's simplify this a bit. What we have here is, let's see, R2 by R. Okay, so we have here is R2 by R1 plus 1 B sub A minus R2 by R1 V1. Okay, and for convenience's sake, and we'll see later, it does make the formula easier. So let's factor out an R2 by R1. Okay, let's factor out that. So what we have is R2 by R1, and I'll put this in large brackets. Okay, what we have here is, let's see, 1 plus R1 by R2, right? If we factor that out from 1, we'll get the inverse of that here. So this is V sub A minus minus V sub 1, just V sub 1. All right. So this was a lot of simplification, but we're not done yet. We have this unknown node voltage right here. Okay, we have this unknown node voltage right here. Okay, but actually this is not unknown. Still, I mean, it's not unknown now, because we saw that this has to be equal to this, right? This V sub A, this node voltage is the same as the other one that we found, and it's equal to this expression. Okay, and the good thing about this is there's no more unknowns here. You know, everything is known about this, and so we should be able to go to the home stretch, as you'll see. Let's substitute that, okay, right here. So R2 by R1. Okay, so here what we have is, let's see, 1 plus R1 by R2, and V sub A, okay, is this R3. Okay, R3. No, wait, that's R4. Yeah, that's R4. My bad. R4, right? I'll just confirm. Yeah, it's R4. R4 divided by R3 plus R4 multiplied by V V sub 2 minus V sub 1 minus V sub 1. All right. So we're essentially done. Okay, just to make this formula more presentable and especially easier to remember, what I'm gonna do is, this is basically part of the numerator of this fraction, and also I'll divide this fraction by r sub 4. Okay, so if you do that, what you get is, and this is I think the most presentable that you can actually make this formula. It's still it is more complicated than all the ones that we've seen. It takes a bit more effort to remember, but yeah, this is as far this is as presentable I think that we can make it. So here what you'll have is 1 plus r1 by R2. This is the numerator. The denominator will be, so here you got 1 after divided by R4, and here is, let's see, this will be 1, this would be R3 plus by R4. So 1 plus R3 by R4. All right. So this is multiplied by V2. Okay, and this is and we subtract V1 from here. Okay. So this is the formula for our differential amplifier, and it's actually as simple and easy to remember as we can make it. At least that's what I think. I don't think there's a simpler form for it. But on a side, well, not a side note really, but we can under a certain imposition, which sometimes we do need in our system. This formula does simplify. Okay, not as it is, but if we make a certain implication, like here. So you have two inputs, right? As I was saying, first thing, I should have said this a while ago. So one thing is clear, is why this is called a difference amplifier. Okay, because we have the negative right here. So they do they do have their coefficients V2 and V1. Okay, but the main thing is that we're able to subtract one voltage signal from another. So that's the specialty of this amplifier. And also, under if we do have a certain requirement, this equation can become simpler. That requirement is, so see here we have two inputs right here, right? We have our v1, we have our v2, and we get some output. If we need the output to be zero, if we necessarily need the output to be zero, so I'll write that down. If if we necessarily need V output to be zero, okay, when our two input voltages are zero, well, supply voltages are zero, and this is required for it is required for many systems where when these two inputs are inputs or sources, whatever you call them, supplies, when they are zero, we would need the output to be 0 volts. Okay, and if that is a requirement, this equation can actually be made simpler. Okay, so let's just think about it. So our V output, okay, which is basically this. So I'll write that here. This is, whoops, let's see, yeah, this is our V output. This is equal to this. Okay, so it has to be zero. It has to be zero. We're saying that this is a condition that we need right now. So if this is true, v1 minus v1 equals v2, and that is, or in other words, I need to fix my speech. So this is the same as this. So what we are saying is this has to be true when this is true. Okay, this has to be true when this is true. Okay, so let's just look. Okay, I should have written v2 minus v1 equals 0. Anyways, okay, v2 minus v1 equals 0. v2 minus v1. Oops, what's happening? Okay, v2 minus v1 equals 0. Okay, so same thing really, but what I'm trying to do is pattern match right here. So we want this to be 0. Okay, we want this to just disappear when this is true. Okay, when this is true, what we have right here, okay, this is just some coefficient. Okay, this is some coefficient. Okay, does so that's just an amplification factor. What we have right here is pretty similar to this, right? Okay, if we pattern match, it's pretty similar to what we have right here, except the coefficient of this is -1, as it's right here. But the only thing is the coefficient of this isn't 1. Okay, it looks different, but since we're implying that when this is 0, this has to vanish, we can also imply that these two must be the same, right? These two must be the same. Okay, so what we have right here must be, well, the coefficient here is 1. Okay, what we have right there uh, must be equal to 1, right? So let's do that. Let's actually try to do that. Okay, so what we have as the coefficient of v2 right there, which is 1 plus r1 by r2, 1 plus r3 by r4. This has to be equal to 1. Okay, that's what we're saying. It needs to be for our condition to be true. Okay, so if this is the case, we can multiply both sides by the denominator on the left. We have 1 plus uh, r1 by r2 equals 1 plus r3 by r4. The ones cancel out, and we have is this condition. Okay, what we have is this condition. We need r1 by r2 to be equal to r3 by r4. Okay, so this needs to be true. This needs to be true. If we need the output to be 0, just disappear when our two supply voltages or supply signals, they are equal to each other. All right, that's what we found. And the ratio of R1 and R2 needs to be equal to the ratio of R3 and R4. And more importantly, this is kind of like, this is kind of like a test to see if uh, our amplifier does meet that condition, and when designing this is useful. But what does this equation simplify to? Well, as we said, if this is true, the coefficient of this has to be 1. Okay, the coefficient of this has to be 1. Okay, in this equation. So let's just do that. Let's just say that, let's just put 1 right here instead of that mumbo jumbo that we have. So what we have uh, is V output equals R2 by R1 multiplied by just 1 into V2, or just V2 minus V1. All right, so this is much simpler. If we need this to be true, our equation actually boils down a lot, and it's much simpler. This is, this is your gain. This is, you could say, this is your gain. Okay. You have some gain, which is the ratio of R2 and R1, also the ratio of R3 and R4 actually. Okay. And multiplied by the difference of the two voltages, all right. So with that done, and again, I'd like to talk some bit more about this. The thing is, there's kind of like some argument or controversy about the naming here and all. Like, some people would say that only when this is true, like this is necessary for this to be the difference or differential amplifier. So only this is only this something which meets this criteria and has this formula, that would be the differential or difference amplifier. And this one is just some circuit that does something. Okay. And what Wikipedia says, I like that one a bit better actually, is uh, although this one you could say it's the ideal difference amplifier or differential amplifier, and this one is kind of like the more practical version. I actually like this one better. I don't think it's fair to exactly qualify what we have right here, like the general one. I mean, it's not fair to disqualify that as the differential amplifier. So we're gonna roll with that. But basically, I think you can see the purpose of this, this circuit in general. Um, Aside from the coefficients and all, what it does is it takes the difference of your two input voltages. They would be scaled up or down a bit, okay, depending on the resistances, and then it amplifies that and gives you an output. Okay, it amplifies that and gives you an output. I uh, actually like to remove that. Okay. So, uh, all right, so let's actually practice some math problems, some circuit problems. The first one I have right here is this one. Okay, so let's see. First thing is, well, in any of these problems where we are dealing with a differential amplifier, and we're trying to solve it, the first thing we should see is actually test the ratio of the resistances. First thing, I'll label them. So this is R1. Okay, this is R1, this is R2, and this is R3, and this right here is R4, right? And again, wait, that would be true. That would be true if I did not forget to label this. I'll do this now. This is your inverting input, and this is your non-inverting input. And yes, as you can see, this circuit does match up with that. Just the voltage sources, okay, or supplies are cells here. Okay, later we'll definitely do problems with with supplies other than cells. We did one before, but we'll do more of them when we deal with multiple op amps. Anyways, that's for later. Um, and yeah, I just pattern match the resistances with what we have here. So the non-inverting input side from left to right, okay, from V1 up to here. Okay, so this is R1 and R2. Okay, and similarly, this is R3 and this is R4, and this should be my ground, my virtual ground. All right. So, uh, well, we label them. Now we need to test for, just to see if, we have that simpler situation we talked about. Okay. For that, we need to check whether the ratio of the resistances are equal or not. So, R1 by R2, okay, I'll do that here. So, R1 by R2 is equal to what? 8 kilo ohms divided by 72 kilo ohms. So, basically 8 by 7. 8 by, so wait, 72, 8 by 72, which is 1 by 9, which is basically 1 by 9. All right. And what about R3 divided by R4? What about R3 divided by R4? That is going to be equal to, let's see, we have R3 is 2 kilo ohms, R4 is 18 kilo ohms. So that's going to be equal to 2 by 18, 2 by 18, which is the same as 1 by 9. So in fact, these two are equal. These two are equal. It does fulfill that condition that we talked about. R1 by R2 equals R3 by R4. And if that's the case, our formula is much simpler. Okay? Our formula is much simpler. It's gonna be equal to, let's see. Also, This is and we should also label these. So this is gonna be the one, the voltage that's kind of like connected to or corresponds to the non-inverting input. That's our V2. We need to be careful about that. And the one corresponding to our inverting input, that's V1. Okay, that's V1. Okay, so we see that V1 is this and V2 is 14 volts right here. So let's actually solve this problem. So output voltage, which is what we need to find, is gonna be equal to, okay, we have R2 by R1. This we need to be careful here. In that formula right there, we have R2 divided by R1. Okay, R2 divided by R1. All right. In both of these, actually, the factor outside. So this is, we are not gonna have 1 by 9. It's actually the inverse of this. So we are gonna have 9 right here. Okay, we're gonna have 9 right here, the inverse of this, multiplied by V2 minus V1. Well, V2 is 14. V2 is 14, and V1 is 9.5. V1 is 9.5. All right. So what we get right here is 9 multiplied by 4.5. 9 multiplied by 4.5. And this is going to be equal to, let's see, 36, and half of 9 is 4.5. That's 40.5 volts. That's 40.5 volts. All right. So this is our output voltage. We solved that problem fairly easily. But actually, need to be aware that this was only well, the other, even if it is what I'm trying to say is, we could only do it so simply because the ratios were equal. Okay, if suppose say our let's see, instead of just, if we make just a single small change right here, suppose that this is, instead of 18 kilo ohms, this is 20 kilo ohms, the ratios wouldn't be equal anymore. We'd have to use that big formula right there. So still shouldn't be reluctant to do that, and honestly it's not really that difficult. Anyway, so this problem is done. I'd actually like to do a design problem now. Let's try to do that. So what I have right here is, I wanna and I'll already give you a heads up. This involves the general circuit where that ratio isn't actually equal. Anyways, so what I wanna do is find a circuit. We find a circuit that fulfills this criteria, an op-amp circuit, an amplified circuit that takes two input voltages, okay, two input voltages or signals, V2 and V1, okay, and gives me an output which is equal to 2V2 minus 3V1. All right. So I think you can see that this is going to be, based on some minus right there. Okay, this has to be, if we want to do it using a single amplifier, there is a way to do it using multiple amplifiers, but we'll study more of that when we do cascaded amplifiers. That's for later. So this is, if you want to do it using a simple single amplifier, this has to be our differential amplifier. Okay, so for that, we don't know if that ratio is true or not, so we need to use this, okay, the general formula. Here, wait, sorry, this is our general formula. I should have kind of like boxed this out from the rest. All right. So what we have right here, the coefficient of V1, it actually isn't, it's not actually -1. Okay, I factored out this. The coefficient of V1 is actually R2 by R1. All right. So the coefficient of V1 is actually, where did that go? Okay. Coefficient of V1 is actually R2 by R1. Negative R2 by R1 actually, and this is also the same as -3. This has to be. So for our differential amplifier, R2 by R1 is equal to 3, right? R2 by R1 is equal to 3. Okay, I cancelled out the minus signs, but anyways, next what we have is, let's see what's the coefficient of V2. What's the coefficient of V2? It's R2 by R1 multiplied by, whoops, this one. Okay, R2 by R1 multiplied by this thing. R2 by R1 multiplied by this thing. All right, so let's do that. So let's see. I'll actually write this down first, and then I'll simplify this a bit. So we have R2 by R1 multiplied by 1 plus R1 by whoops 1 by whoops. Okay, 1 plus R1 by R2 divided by 1 plus R3 by R4, and this has to be equal to 2, right? This has to be equal to the coefficient right here, which is 2. All right, so here we can make some simplifications based on what we found right here. One thing is R2 by R1, this is just equal to 3. Okay, this is just equal to 3. R1 by R2, it's the inverse of that, it's 1 by 3. All right, so this boils down to, and actually 3, and we have 1 plus 1 by 3, 4 by 3, we'll have 4 right here. Okay, so 4 divided by 1 plus R3 by R4 equals 2. If I do some algebra right here, we get 1 plus R3 by R4. This has to be equal to 4 by 2, right? 4 by 2, which is 2. Or, this is the important one. This is what we get at the end. The ratio of R3 and R4, the ratio of R3 and R4 needs to be equal to 1, or in other words, they need to be equal, okay? Or in other words, I guess that's the most useful way to write that. Or in other words, R3 equals R4, and what we have right here is R2. R2 needs to be triple, okay, triple of R1. All right, so yeah, that's basically, these are our conditions for the circuit that the differential amplifier circuit we'd like to design. There's no specific solution, okay. As long as we have the resistance on hand and it's reasonable, we can create any circuit that differential amplifier circuit that satisfies these two conditions. All right, the R2 being triple of R1, R3 being equal to R4. So let's actually construct a circuit. Okay, just one example circuit. Okay, and for that, actually, let's say we also impose something else on this problem. The fact that the resistances, okay, like in this circuit, the resistances leading up to the inputs, okay, they need to be equal, okay, or R1 needs to be equal to R3. Let's say that needs to be true, okay. That could be in the question, like if they said the common mode input resistance is suppose say let's say R3 equals R1. Let's pick 40 kilo ohms. Okay, let's pick 40 kilo ohms. Okay, suppose both of them need to be equal to 40 kilo. Okay, R1 needs to be equal to 40 kilo ohms. I just said that. Okay, I just said that. So and R3 same needs to be 40 kilo ohms. Okay. R2, as we saw, needs to be triple, okay, or yeah, triple of R1. So that needs to be 120 kilo ohms. That needs to be 120 kilo ohms. And R4 right here needs to be the same as R3, which is 40 kilo ohms. So voila, we have our circuit which meets this condition. It's actually just one example circuit. As I said, as long as you fill the two criteria, any differential amplifier circuit is valid. And also this is just something that I just imposed later on, okay. Just as to find a circuit like this. But anyways, enough of me blabbering. Pretty interesting. I want you to understand the essence of this circuit. No matter from where, okay, maybe it's from another op amp, or maybe these are from cells, okay, or another type of circuit, okay. This differential amplifier circuit, what it's gonna do is take two voltages from anywhere, okay, two voltages, and it's gonna It's gonna multiply the, V2, the this one, okay, V2, one of the voltages by 2, multiply the other voltage by 3, and find their difference. Find their difference. So it's a pretty special circuit, right? It's pretty special circuit. It does quite a lot, actually. It does, quite a lot. This single circuit. That's why I find, even though differential amplifiers are slightly harder to deal with, these are pretty fascinating, right? All right. So that should be the end of this video. Yeah, I think, if even if I do another problem, I might separate that. Yeah. So goodbye and study smart.